Here's another example where we have two fractions, and this is quite obvious that our left side is more complex than our right side. So we're going to try and simplify the left side and see if we can get 0. Because we have two fractions where we're adding, we're going to try and find our LCD again. So our LCD would be this denominator times this denominator, since they have nothing in common. So we have to multiply sine x plus sine y by cosine x cosine y, and do the same thing to the top. So here we're going to multiply by cosine x plus cosine y. And on the top we're going to multiply by cosine x plus cosine y. If we multiply this times this, we end up with cosine squared x minus cosine squared y. And in our denominator, we have cosine x plus cosine y times sine x plus sine y. Here, we're going to have to multiply this one by sine x plus sine y. So you're going to multiply by sine x plus sine y. So we'll multiply this by sine x plus sine y. So this will now give us plus sine squared x minus sine squared y. And since our denominator is the same, we can go ahead and combine both of these over our LCD. Now if we rearrange the top, we have sine squared x plus cosine squared x minus sine squared y minus cosine squared y. We still have our denominator. If we still work with our numerator, we know that sine squared x plus cosine squared is equal to 1. So all this becomes 1. If we factor out a negative 1 from this, it becomes minus sine squared y plus cosine squared y. Once again, sine squared y plus cosine squared y will be equal to 1. So this becomes 1 minus 1 on the top, which gives us a numerator of 0. Since our numerator is 0, it's irrelevant what our denominator is. But here, let's write sine x plus sine y. But since our numerator is equal to 0, all this becomes 0. So we have proved that our left side is equal to our right side. Here we have an example that includes our arcsine function. We know this is asking us for the angle whose sine is x minus 1 over 4. If we go back to our right triangle, we know sine is equal to the opposite over the hypotenuse. So our opposite here is x minus 1, and our hypotenuse is 4. To find our adjacent side, so our angle is u, we know that our adjacent squared plus the opposite squared is equal to the hypotenuse squared. So this becomes a squared plus x minus 1 all squared is equal to 16. If we subtract x minus 1 squared from both sides and take the square root, we have a is equal to the square root of 16 minus x minus 1 squared. So here our adjacent is 16 minus x minus 1 all squared, and we're finding the square root of all of that. Now we're required to find the tangent of that. So tangent is equal to opposite over adjacent. So our tangent then would be x minus 1 over our adjacent, which is the square root of 16 minus parentheses x minus 1 all squared. And we can see that that is equal to the right hand side of our identity. So here we have just proved that this identity. Here we're verifying that secant of x to the 4th power times tan squared x is equal to, in parentheses, tan squared x plus tan to the 4th power of x all times secant squared x. Since the right side will look a little more complicated, we will begin by working with this side. We can see that inside the parentheses we have tan squared x that common to both terms, so we could factor tan squared x from our parentheses. So this will give us 1 plus tan squared x times tan squared x, and we still have the secant squared x here. We know from our fundamental identities that 1 plus tan squared x is equal to secant squared x. So we can replace this with secant squared x. So now we have secant squared x times tan squared x times secant squared x. Or secant squared x times secant squared x will give us secant to the 4th power of x times tan squared x, which is exactly what we have on this side. Here we'll be using our cofunction identities to simplify this expression without the use of a calculator. So we have cos squared 20 plus cos squared of 52 plus cosine squared of 38 plus cosine squared of 17. We know of our cofunction identity that cosine of pi over 2 or 90 minus theta is equal to sine of theta. So cosine of 20 is the equivalent of sine of 70 degrees. Similarly, the cosine of 52 degrees would be equal to the sine of 90 minus 52 would be 38 degrees. So now we have sine 70 degrees plus sine squared 38 degrees plus cosine squared 38 degrees plus cosine squared 70 degrees. If we group our similar angles, we have sine squared 70 degrees plus cosine squared 70 degrees plus sine squared 38 degrees plus cosine squared 38 degrees. We know from our Pythagorean identities that sine squared of theta plus cosine squared of theta is equal to 1. So since our angles are equal, all this here is equivalent to 1. Similarly, this is equivalent to 1. So this becomes 1 plus 1, so our answer is 2.